Why is PowerPoint frozen? Come on. Now you can let me move? All right. So we have three logical operators, and, or, and not. We're about page 40. So we have and, or, and not. And means both sides have to be true. If I am hungry and I have money, let's get a Snickers. If I don't have money or I'm not hungry, I'm not going to be able to get the candy bar. Or there's no reason to, right? If I'm not hungry, I'm not going to get it. So to express that more like code, I just need to remember that in this language, unlike Python, and is represented by two ampersands, a shift to the 7. And or is represented by two vertical bars, the backslashes. And I guess while we're at it, we'll mention that not is represented by an exclamation mark. So I could do something like this. If hunger greater than 0 and money greater than 0, C out less than, eat a Snickers. Backslash n. No, I'm not receiving financial compensation from the Snickers company. Here we go. So if money is not greater than 0, then this part's false. And means both sides have to be true before the result is true. And our hunger could be maxed out to the max, but if money is not greater than 0, if we don't have any money, then the expression is still not true. So we don't get to eat the Snickers. So for and, both sides of the expression must be true. Or means just one side or the other. One side or the other of the expression must be true. If I am sick or I am tired, I get to stay home. My boss is really nice, lets me stay home if I'm sick or tired. Now this isn't a rehash of a prior lecture, is it?
You mentioned a lot of it.
Okay. Then I'm not going to mention a lot of it, and we're going to go on to the next topic, but I'm going to go ahead and finish writing this. So, if sickness greater than 0 or tiredness greater than 0, C out less than, stay home from work. So the truth table for each of these. Have I drawn two tables? I really don't want to keep doing stuff that I haven't already done.
Well,
is that a yeah? Well, it won't take too long. So the truth table for and looks like this. If you have x and y and you have a result, I'm going to treat zeros as though they're falses and ones as though they are true. So a 0 and a 0, the result is a 0. If that's not true and that's not true, the result has to be false. If something is false but the other thing is true, well, and meant that both of them had to be lit up for it to be true, and they're not, so it's still not true. If that side is true and this one is not, if x is true and y is not, well, and meant that they both had to be set. They're not, so it's still false. It's only when both sides of the AND are true that we get a true out of it. Now we could rewrite that, replacing the zeros and ones with trues and falses, and we would see something that look like this, right? They just have theirs flipped. I put 0, 0 up at the top of mine. They put false and false at the bottom of their chart, but it's the same idea. AND means that both sides have to be true before the result is true. Otherwise, every other case is false. Now, OR is a little bit different. OR means one side or the other. So the only time OR is false is when both sides are false. Because otherwise, right, if X is true, the result is true. If Y is true, the result is true. If they're both true, the result is true. So the truth table for OR looks a little bit different. X or Y, and the result 0, 0. Well, neither one of them are true, so the result is false. 0, 1. Well, one of them is true, so our result is true. 1, 0. It's still true. And 1 and 1, the result is true. Now, if it's bugging you to see zeros rather than, you could just copy and paste this and edit it and replace all the zeros with F's and all the ones with T's, if that helps you think of it better. I could do the same thing for the OR truth table. All the zeros become F's. All the ones become T's. Trues and falses. Okay. Then there's such a... Oh, and not X, right? That just flips it, right? So if X was true, if X was false, it becomes a true. If X is true, it becomes a false. So false becomes a true, and then true becomes a false, if you're doing not. Now I wrote it out this time as zeros and ones because we're going to be talking about bitwise and bitwise OR. Oops, but that means going through it bit by bit. Say we have this number, 48, and we have another number, 3, and we want to do X equals 48 bitwise ORed, how do you spell ORed, with 3. All right. Bitwise means that instead of doing a logical true or false, it actually looks at each bit in turn. My first shot, I'm just going to write it on the board. Sorry, folks, for watching on camera, but then I'll reiterate it in notepad. So, great. 48. Did I show how to convert from decimal to binary? You just keep dividing by 2. If I have the number 48, great, people on camera aren't going to be able to see it. 48 divided by 2 is 24 with a remainder of 0, right? 48 divided by 2 is 24. It was even, so we didn't get anything else. And then 24 divided by 2 is 12 with a remainder of 0. 12 divided by 2 is 6 with a remainder of 0. 6 divided by 2 is 3 with a remainder of 0. 3 divided by 2 is 1 with a remainder of 1. And then 1 divided by 2 is 0 with a remainder of 1. And then you just write these from top to bottom, from bottom to top. So this 48 is 1, 1, and how many zeros were there? 1, 2, 3, 4. So 48 wound up being, after we kept dividing by 2, 48 divided by 2 became 24 with a remainder of 0. 24 divided by 2 is 12 with a remainder of 0. 12 divided by 2 is 6 with a remainder of 0. 6 divided by 2 is 3 with a remainder of 0. 3 divided by 2 is 1 with a remainder of 1. Kind of like modulus 2, right? And the 1 divided by 2 was 0 with a remainder of 1. And so the answer of it is 1, 1, 0, 0, 0, 0. So 48 is 1, 1, 0, 0, 0, 0. And if we wanted to pad it out to a full byte, we could, right? You know, we could tack on 2 more zeros to give it 8 bits. I'm not sure why I'm wanting to do this on the board, but I kind of want to. And what about that other number, 3? Well, I'm not going to make us work through it. If 48 is that, and 3 is just, we know there's a 1 involved, we know there's a 2 involved, and we know that the rest of them are 0. Okay, now we're going to bitwise OR. Bitwise OR. I'm going to line them up, one on top of the other. And then bit by bit, I'm going to do a little OR on them. First, I'm going to talk it through. A 0 or a 0. According to our truth table, if you have 2 zeros, what's the result? For OR, 2 zeros is a 0. So, I'm not going to be able to. Forget it. I'm going to stop writing on the board and I'm just going to do it up. So, 0 or a 0. They're both false, so the answer is false there. How about this one? Are either ones in these columns set to 1? Nope. So that's a 0. How about the next one? Are there any 1s in that column? I'm pausing real long so that gives you a hint.
Yes.
Yep. So, and there's a 1 in that column. There aren't any 1s in that column. Now I'm not counting the number of 1s, I'm just making sure that at least 1 is lit up, that there's a 1 in that column. No 1s in that column, so that's a 0. Are there any 1s in this column? Yes, there are. Are there any 1s in this column? Yes, there are. So if we did bitwise 48 or 3, then that's the answer. And I don't remember what that is, but we could add it up. Counting from right to left, that's a 1, that's a 2. There's no 4s, there's no 8s, there's a 16 and a 32. So if I add those up, that's a 32 plus a 16 plus a 2 plus a 1. 48, 49, 50, 51. Now that's kind of counterintuitive. No, I guess it's not. In this case, it looks like addition, because 48 and 3 did come out to being 51. So 48, bitwise OR, which is a single pipe. Bitwise is a single bar. 3 is equal to 51. Now that looks like addition. Why is that the case? Because there aren't any bits that are overlapping. And so our answer had a 1 in it and it had a 2 in it. It didn't have any 4s and it didn't have any 8s, but it had a 16 and it had a 32. And so it did add up like that. Well, it's not going to always work like that. Yes, sir.
So say that was 49.
Yeah, we're going to, exactly. Let's do 49 now. Exactly. I'm just going to copy and paste this stuff right here and do it again. So bitwise OR 0, 0, 1, 1, 0, 0, 1, but I made that a 49, so that was lit. Man, this party is lit. All right, so 0, 1. How about this one? Yes, OR means one or the other or both. So there. And if we added those up, that's still going to be equal to 51. Those same numbers add up to 51.
You never changed your 48.
I changed it there and I did not change it there. Thank you. Thank you very much. Okay. So in this case, 49 ORed with 3 is also equal to 51. we had an overlapping bit there. It just didn't get taken into effect, and I don't know how to say that. The reason that these added up is because none of the bits were overlapping. Here we had an overlapping bit, so one of them didn't get summed into the total. But summing and ORing, I don't really want us to think in those terms. How about if we had something like this? I'm just going to make up a pattern. I don't even know what the numbers are. There. Then what's our result going to be? If we do a bitwise OR, which is what that symbol is, do we have anything in the first column? Is that a 0 or 1?
0.
0. How about the second column? 1. Third column is a 1. Fourth column is a 1. Fifth column is a 1. Sixth column is a 1. Do we have anything in the seventh column? Nope. But we do have something in the eighth column. And if we added these up, this is a 4 plus an 8 plus a 16 plus a 32. Like I could do that in my head. I think I could. 12, 44. Oh, forget it. Google is my friend. I think it's 60. Oh, you're not going to... Yeah, all right. So that was a 60. And this is a 1, but no 2s, no 4s, no 8s, no 32. But it does have a 6. 1, 2, 4, 8, 16. It has a 32 and it has a 64, which is a 97 total. And then if we added this up, that's a 1 plus are there any 2s in it? We've got to look from the right. There's a 1, but there's no 2s. But there is a 4. There's an 8, fourth place. And there's a 16 and a 32 and a 64. And again, I'm lame and not going to do it by hand. I'm going to come and type that. Okay, so 125. So in this case, 60 bitwise OR 97 equals 125. Now, there's no mathematical way that we could have predicted that, right? I mean, not with addition, right? 60 plus 97 equals 125? No way. But when the bits were all mashed together like that, they did. So that's bitwise OR. Bitwise AND, both zeros have to be lit up before the result. Excuse me, both bits have to be set before the result is set. So if we come back up here and grab our 48 and our 3, this is almost going to be a waste of time because the answer is going to be straight zeros all the way across. But let's prove that. If we have 48 and we have 3, since it's an AND, both top and bottom have to be set to 1 for the result to be 1. 0, 0, nope. There's no matching ones there. 0, 0, nope, none there either. 1 and 0, nope, they're not both set. Oh, why did I type a 0 there? 1 and 0, nope. Don't have 2 bits there. Nope, not there. Not there. We can see where this is going. Nowhere did we have any matching bits set. So 48 single ampersand 3 equals 0. All right, now that was boring. Let's do one of the others. This one doesn't have any overlapping bits either. So it would also be 0 all the way across. This one, are there any overlapping bits in these two numbers? There's 1 right in the 1's place. So if we did it, we'd get the answer of 1. I'm going to not do that one. I'm going to come and I think I'll just make one up. Let's make one up that looks like this. 10 11 0 0 0. And then we're going to do 0 0 1 0 0 0 1. And we're going to OR those two numbers together. So now we're going to do bitwise OR. Wait, we've done bitwise OR. We're doing bitwise AND. I reserve the right to change my bits. I want some overlaps here. That one only had one overlap. I'm going to choose something that has more than one overlap. Okay, there we go. So we're going to bitwise AND them. This leftmost column, does it have a matching pair of ones? Nope. How about the next one? Yep. How about the next one? The third column does not have a matched set of ones. So it's a 0. But the fourth column, does it or does it not? Yep. How about the fifth column? That column. Do we have 2 ones in that column? Nope. Alrighty. I don't think we have any matched bits going out to the end. So that's the result of ANDing these two patterns together. So that's a 1, that's a 2, that's a 4. 8 plus 16, so this equaled 32. And this equaled 1 plus no 2s, no 4s, no 8s. 16, 32, and 64. Which is 80, 113. All right. So the result of ANDing and ORing those two pieces of data were 113. So 32 ampersand 64 equaled 113. And again, there's no simple mathematic operator that would have done that. Multiplication or addition or subtraction would not take that and get that out of it. So why would you want to do that? Well, what if you had some number, some transmission system, and you only cared about the first 4 bits of the number and not the last 4 bits of the number? Or what if you had something and you wanted to extract the value of the first 4 bits and then later you wanted to extract the value of the last 4 bits? So what if I had this series of data and I wanted only the last 4 bits? I could AND that against this pattern. And it would tell me the last 4 bits, and the rest of them would all be set to 0. Why would the first 4 be set to 0? Because there's no way they could be matched pairs since they're all 0. So we know the result is, and then we can actually start checking. 1 and 0, nope, we're trying to do and only one of them is set, so that's not true. 1 and 0, nope, only one of them is set, so that's not true. 1 and 1, are they both set there? Yes, they are. And 1 and 1, both set there? Yes, they are. So now if we look, we managed to get the last 4 bits out. Everything else was set equal to 0. So we extracted the last 4 bits, and then the answer was 3. Whatever that number was. If we get the last 4 bits, it's equal to 3. We could do the same thing, taking this and ORing it to get the first 4 bits. 1, 1, 1, 1, the rest of them being zeros. Well, we know the last 4 things of our answer, whatever they are going to be zeros, but the first 4 we have to check. So 1 and a 1 is the first column a set of matching 1s? Yep. How about the second column? Are they matching 1s? Nope. How about the third column? Yep. The fourth column, nope, and then the rest of them, nope. So that's a 16 plus a 64, no, a 128 and a 32. I can't do that in my head. You'd think I could. This is pretty lame. But anyways, 128 plus 32 is 160. So whatever these two values were, when we bitwise AND them together, we got 160. So we took this number and we bitwise AND it against, what's this? That's a 1 plus a 2 plus a 4 plus an 8, so that's a 15. 15 gave us the last 4 bits. Here we have a 16, 32, 64, and 128, whatever those are. 16 plus 32 plus 64 plus 128. That's 240. So by ANDing it against 240, we extracted the first 4 bits. And we found out that Well, what if, okay, that's enough what ifs. Let's write a little bit of a program where we get to type in two numbers and it will AND them against each other. So I think today is lecture H. Alrighty. I don't really think there's a data type called a byte. Let's find out if there is. Let's find out if there's an unsigned byte data type. Unsigned byte. X. Nope. Unsigned char. Does it support a data type called unsigned char? Seems to. I think a char is unsigned to begin with. Alright, my fear is that if I do something like this, x is equal to 65, and then I print it out, that it's going to print out a, because it knows it's a character. Yeah, I printed out a. Alright, that's not what I wanted. I would have to cast that to an int in order to print it out. In which case, why bother making it an unsigned anything? Forget it. Just going to use ints. Alright. So int x comma y. Let's ask them for two values. Cout less than. Let's bitwise dash and two numbers. Not nombres. It's not Spanish. Numbers. What is x question mark? Space greater than end quote semicolon. Cin greater than x. And then cout less than. What is y question mark? Space greater than end quote semicolon. Cin greater than y. So let's get our result. Int result equals x single ampersand y. And we may as well print that out. Cout less than quote x ampersand y equals space end quote ampersand result ampersand ENDL. Now we can use this to back check the notes that I took. Alright, bitwise two numbers. Well, what is two of the numbers that I used? I did 32 and 64 and got 113. I'm going to see if I did that math right. So, x is 32, y is 64, and it said that x and y is equal to 0. Well, then it wasn't 32 and 64. What did I do reading my notes? Oh, because that's definitely not a 32. Don't know what it was, but it wasn't a 32. I guess I should figure it out. There's no 1s, there's no 2s, there's no 4s, but there's an 8 and a 16 and a 64. Which is equal to 88. And this one, so that was actually an 88 right there. Where in the world did I get this? These numbers have nothing to do with these numbers. Well, glad I'm revising my notes because that was crazy. I'm sure you got the concept even though I wrote something crazy down here. Alright, maybe it's time to start using a Windows calculator. Calc. Alright, going to enter these numbers in binary and switch it over to decimal. That first one is an 88 as predicted. How about this one? Switch back to binary. Paste it. Switch back to decimal. That's 113. Then what is this one? Switch to binary. Paste it. And you know how I got here. I just ran the Windows calculator. Not useful for your Mac guys, but you can download a programmer's calculator if you haven't already. And then switch it. View programmer mode. Go to binary. Paste my mystery number. Switch it back to decimal. And it's 80. So in this case, 88. Single binary, single bitwise AND against 113 equaled 80. Now to run my program and see if I get that. (88) and 113. So 88, 113 gave me a result of 80. And this 88 is spurious. I had a final print statement that's not necessary. I'm going to delete that final spurious print. I'll try a few more. I know I did a few more examples. I hope they weren't as messed up as that one. Like here, we ANDed something with 15 and got 3 out of it. So let's find out what this one is in decimal. Binary, paste. Decimal is 163, so that was 163. We're going to bitwise AND 163 with 15, and we ought to get 3.
You deleted the wrong print.
Thanks. All right, yeah, I deleted the wrong print statement. Okay. (163) and 15. Got 3. Okay. We could do the same thing to OR them if we wanted to. All we'd have to do is change the ampersand to a single vertical bar and it would display them ORed together. Alright, one more thing I want to talk about is shifting to the left and to the right. What does shift mean? If you have this 0, 0, 0, 1, and if you shift that 1 to the left, that means that everything rotates 1 to the left. And so we would get 0, 0, 1, 0. And if we shifted it again, it would become like that. And if we shifted again, we would get that. And if we shifted it again, well, it can't be held in our 4 bits. So we would just get, you know, that. How about shifting to the right? What if we had this number? 0100. Shift 1 to the right. Well, that 1's going to start migrating to the right. And if we did it again, it migrates to the right. And if we do it one more time, it falls off the edge into the bit bucket. It's gone. Now, we don't have 4-bit numbers, but we have 8-bit numbers. What if we had this number? 1, 2, 3, 4, 5, 6, 7, 8. And I wanted to shift it to the right 2 times. Well, that means that everything is going to go rotate twice to the right. And so we're going to get this. And if we shifted it to the left twice, then the ones would have wound up right here instead. Now, why might you care about that? Well, back up here, when we extracted the first 4 bits, we got the first 4 bits, but they were padded out with some zeros at the end. We could shift this number to the right 4 times, and then we would just get a nice pretty 1010, which is, in fact, the first 4 bits. So if we had taken this number and ANDed it by 240 and then shifted it to the right 4 times, we'd get what the first 4 bits were. So a single, let me make absolutely sure this is the case, but a bitwise shift should just be a single less than rather than a double. Bitwise left C++. You gotta be kidding me. It's the same thing as the IO stream redirectors. All right, it's the less than, greater than, greater than. So notice one thing here is that if you had the number 0001 and you shift it 1 to the left, what is it equal to now? 0010. And then say I shifted it to the left again, what is that equal to? Zero, 1, 0, 0. And then if I shift it to the left one more time, what's it become?
1, 2.
Yep. And so what is this equal to? That's a 1. That's a 2. That's a 4. And that's an 8. Cool. Looks like it was doubling. It is. If you do this, that's a 2 and a 4, so that's equal to a 6. Right. I know there's no 1s, but there's a 2 and there's a 4, so that's a 6. And then if we shift it to the left, then if we shift it to the left again, but now we've hit the edge. We've had some we've had some overflow here. We've had some overrun. But at first it worked. If we add these up, there's no 1s, there's no 2s, but there's a 4 and an 8, so that's a 12. Here we don't have any 1s, 2s, or 4s, but we have an 8 and we have a 16. And 8 plus 16 is 24. But now we have buffer overrun. It's gone off the edge, and so we have a no 1s, no 2s, no 4s, no 8s, but we do have a 16. And then nothing is lit up here. But anyways, if we take a number and we shift it 1 to the left, it's the same as doing integer multiplication by 2. What about the other way? What if you have a number and you're shifting it to the right? What if we had this number? Well, there's no 1s, there's no 2s, but that's a 4 plus an 8, which is a 12, plus a 16, so that's a 38. 16, 28? 1, 2, 4 plus 8 is 12, plus 16 is 28. Okay. And then I shift everything to the right by 1. and then I do it again. So what is this equal to? That's a 1. There's no 1s, but there's a 2 plus a 4 plus an 8. And 2 plus 4 is 6 plus 8 is 14. How about this? There's a 1 and a 2 and a 4. Add those two together and you get 7. But now we're at the edge, and so if we keep shifting, the bits are going to start falling off. That's just equal to a 3. That's equal to a 1. So this is the same thing as integer division by 2. Shifting to the right by 1 is the same thing as integer division. 28 became 14. 14 became 7. 7 divided by 2, rounding down is 3. 3 divided by 2, rounded down is 1. 1 divided by 2, rounded down is 0. So let's play with shifting. Let's ask them for a new value for x. Cout less than quote. We are going to shift x to the left 4 times. Period. Backslash n, end quote, semicolon. Cout less than. What is x? Question mark. Space, greater than, end quote, semicolon. Let them type it in. So Cin greater than x. So result is equal to x, and I want to go to the left, so the arrow should point to the left. I want to shift 1 time. Tell you what, let's declare 4 result variables. Int r1, comma r2, comma r3, comma r4, semicolon. r1 equals x less than 1. r2 equals x less than 2. r3 equals x less than 3. r4 equals x less than 4. And then let's just see out left end shifted dot end quote semicolon, and then let's see out less than r1 less than quote space quote, and then just copy and paste that a couple of times to print out r2 and r3 and r4. r2, r3, r4, and then let's do an ENDL. And we should just see numbers doubled each time, unless we typed in something larger than 2 billion, or that became larger than 2 billion, because we would get overflow. We've already said that an integer, a signed integer at least, can only hold a number of up to 2 billion. So if x is 1 and y is 1 bitwise, and they are 1, we're going to shift x to the left 4 times. What is x? Well, it's 13. Shifted once, it's 26. Shifted twice, it's 52. Shifted 3 times, it's 104. Shifted 4, it's 208. I feel like doing the same thing, shifting to the right, but I don't feel like typing all that in again. Why don't we just take these 4 statements and all of this stuff, everything from R1 equals shift, copy it all the way down to the end except make it shift the other way. So instead of less than 1, it's going to be greater than 1, greater than 2. greater than 3, greater than 4. And this needs to say shifted right, because that's what we're doing, right? And so maybe I ought to go back and retroactively change this part to say shifted left. Maybe I'll say X shifted left and X shifted right. All right, so I'm going to type in the number 256, which is a 1 followed by 8 zeros, binary-wise. Oh, that was just for this part. Okay. We're going to shift X to the left 4 times. What is X? 256. And it kept doubling it. And then as it shifted it to the right, it kept dividing by 2. Now if I type a number that when it's doubled 4 times in a row becomes larger than 2 billion, then we're going to see some overrun. So if we take any value and we divide it by 16, what is 2 billion divided by 16? 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, divided by 16. Okay, so if our number starts off, how many zeros is that? 1, 2, 3, 4, 5, 6, 7, 8. Let's start off with 2 followed by 8 zeros, which is 20 million, I guess. So I'm going to run it again. X is 1, Y is 1, and now I'm going to type in 20 million. No, that's 200 million. Anyways, a 2 followed by 8 zeros. 1, 2, 3, 4, 5, 6, 7, 8. And we see that it shifted past the point where some of the bits were treated as signed bits, and so it flipped to being negative. And then when we kept shifting it to the right, it just kept dividing by 2. So now you know bitwise AND, bitwise OR, shifting to the left and shifting to the right. There's one more called exclusive OR. Exclusive OR means that one and only one bit had better be set. The exclusive OR symbol is that one. So if I had these bits and I wanted to exclusive OR them, then, well, 0, 0, neither one of them is set, so that's a 0. But exclusive OR means one and only one. If there's 2, it doesn't count. In that column, there are 2, so it doesn't count. How about the next column? Yeah, we have 1 and only 1, so that's good. That one is set. The next column, we don't have 1. We don't have exactly 1. We have 2 set, so that's a 0. How about that one? Is that going to result in a 1 or a 0?
1.
Yep, that's going to be a 1 because we have exactly 1 set. That's the case here as well. In that column, there's exactly 1 set. And there. So if we took these two numbers, whatever they are, then we exclusive ORed them, we would get that. Now, I've never had to do that as a programmer. It's more an electrical engineering kind of thing. Doesn't mean there's no reason to ever do it. I just never ran into it. Okay, so we've talked about truth tables. We've talked about ORs and ANDs and shifting to the left and shifting to the right. That is about enough of that. Anybody need syntax error correcting? Did I just go too far without? All right. Looks like I closed all my windows. That's sweet. this is pointless trivia, but if you ever go to iCanHasIP, but has is spelled with a Z, iCanHasIP.com, it tells you what IP address the internet thinks your machine is at. Now that's different than your local internet address. If I come to the command window and I type, what is it? Netstat. My local address is 1055.10.154. Now notice all these numbers in your IP address. Every one of them is between 0 and 255. And we've already seen that come up before. That means that every one of these values, bless you, in an IP address is a single byte. So your IP address is 4 bytes long. It's just that for ease of understanding, we express them as being numbers separated by periods. Now that's called IP4. 4 different combinations of 255 really is not that many numbers. When the internet was being invented during the 70s, it seemed like an astronomically huge number, but it's not. And pretty much the entire IP4 address space has been used up, and they're having to do some real weird tricks routing-wise in order to ever grant anybody more IP addresses and what should fit in there. So there's something else called IP6, Internet Protocol 6, which instead of having 4 bytes for your IP address would give you 8 of them. And so that's vastly gigantic. Just like the difference between a float and a double is astronomically different. Doubling the number of bytes that you have for your IP address. That would fix a whole bunch of routing problems, but then older equipment is not necessarily backwards compatible. Okay, so flags. Seems like I would have already talked about flags, but that's the chapter that that's the page that we're on. A flag is something that is either set and it can be checked later. I'm sure I talked about that. Yeah, okay. So logical operators. And or not. The result is true if both sides are true, both operands are true. Or it's true if either side is true, and not just flips it, reverses the truthiness of it. So our logical operator examples, let's quickly get that off to the side so that we don't get to see it. X is 12, Y is 5, and Z is equal to -4. All right, so is X greater than Y? Well, is 12 greater than 5? Yes. And is Y greater than Z?
Yes.
In this case it is. So true and true, the result would be true. I'm going to put a T there. So that's our prediction. So is X greater than Y? Yeah. Is Z greater than Y? Is -4 greater than 5? No. So, and this is an AND, which meant that both sides had to be true. So that's a true and a false. That evaluates to a false. Is X less than or equal to Z? Is 12 less than or equal to Z? No. So that's definitely a false. How about this? Is Y equal to Z? No, that's silly. And so false or false is false. Okay. X less than or equal to Z? No, that's still not true. X is not less than Z, so that's a false. Is Y not equal to Z? Is that true or false right there? Is it a true statement that Y is not equal to Z? Yeah, that's a true statement. And so, since this is OR, there only has to be one, not both of them set up, so that should be a true. And lastly, since we have some parentheses, we're going to do these stuff inside the parentheses first. Is X greater than or equal to Z? That's true, but then the not flips it. So not true becomes false. Let's take a look, see if we got them right. True, false, false, true, false. So to earn our special interest rate, our income has to, or to get our loan, our income has to be above the minimum income, and we must have been employed a minimum number of years. And that's definitely an OR situation because they used two vertical bars there. So we let them type in the income and we let them type in the years, and then we have this OR statement. If the income is greater than the minimum income or the years of employment is greater than the minimum years, then we print you qualify. Otherwise, we tell them too bad. Pretty neat that you can get the loan just by years of employment. You could be $1 billion in debt and still get the loan just because you've been worked there for the minimum number of years. So logical notes, exclamation mark has a higher precedence. And then ampersand, ampersand, and then or. And did I already say the statement that and is logical multiplication and or is logical addition? Does that sound familiar or not familiar? I'm not hearing a lot of familiar, so okay. Remember our truth table up here? The and truth table? If I come down here, I'm going to paste it again, but I'm going to change it a little bit. What math symbol could I put here and have it look about right? Multiplication or addition? Let's try addition. 0 plus 0 gives us a result of 0. Yeah, sounds great. 0 plus 1 gives us a result of 0. No, that's not right. So we're going to go back and try multiplication. 0 times 0 is 0. Yep. 0 times 1 is 0. 1 times 0 is 0. 1 times 1 is 1. Okay, so this was the and truth table. It worked out that if you replace the word and with the symbol star, it works. So and is logical multiplication. And if you ever go and take a logic course, you become a computer science major at a 4-year college, or maybe they teach this in discrete math, I don't know. But anyways, and is logical multiplication. So if you have the or truth table, way back up here, and we change that to plus, then it looks right. 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 0 is 1. 1 plus 1 is equal to, oh, well, it's still correct because in Boolean math there's only 2 possible states, right? There's only 2 possible numbers, 0 and non-zero, or 0 and 1. So 1 plus 1 is 1. So that means that or is logical addition. And so in a logic class you may see things expressed like this, AB plus CD, meaning A and B, or C and D. Okay, so which has higher precedence, multiplication or addition? According to operator precedence, if you had the expression A plus B times C, are you going to do the multiplication first or the addition? You're going to do the multiply first. Same is true logically. That means that and has higher precedence than or. Since and is multiplication and or is addition, and has higher precedence than or. So if you had this phrase, A is equal to 10, B is equal to 20, C is equal to 30. And we had this. If A is equal to 10, or B is greater than A, and C is greater than B. We'd have to figure out what to do first. Are we going to do the or first, or are we going to do the and first? But we're going to do the and first, and so we would check both sides of it. And is B greater than A? It sure is. Is C greater than B? It sure is. So this whole side evaluates to being true. Then we'd go, okay, now we have an or, and so is this true? Yeah, that's true. Well, that's enough to get it, the whole thing to be counted as true. But we could check the side. Is A equal to 10? It sure is. So, but it wouldn't have mattered. even if this was a complete false statement, this part of it evaluates to true, so the whole thing evaluates to true.
What about the not statement?
Not has higher precedence than anything else. But by the time you start throwing nots in there, like if you had not C greater than B, I would try to find a way of rewriting it. I would say C is less than or equal to B, right? But definitely not has higher precedence than either one of those other two things. So if the value of the expression can be determined by checking just the left side, the rest of it's skipped for efficiency's sake. So my old expression was if hunger greater than 0 and money greater than 0, see out Snickers. Say we were going to repeat this loop 70 billion times. And we wanted to write it so that it took the fewest number of computer cycles. Well, let's say that we are Shaggy and Scooby-Doo and we are hungry way more often than we have money. So of the two criteria, hunger greater than 0 is true 99% of the time. And money greater than 0 is true only 1% of the time. Now we could have worded this two ways. We could word it like this, or we could reverse those two things. And we could say if money greater than 0 and hunger greater than 0. Now if it's something that's going to be checked only once, it doesn't matter which order these things are checked in, right? Because it only takes a nanosecond for it to do it. But if it's running over and over and over and over, and speed is of the essence, then you want to arrange it in such a way that it runs as fast as possible. So if this part is true, it has to check this one. And if this part is not true, it doesn't even bother checking the next one because they both had to be true. So this is conditionally skipped based on whether this is true or false. If this part's false, it doesn't do this comparison. And so that's several steps of the computer CPU that it gets to skip because this one is false. So that means that you want to put the one that is least often true first because you want to rule out as many circumstances as possible. We very rarely have money. So we very rarely will have this triggered to be true. And only the 1% of the time that we happen to have money are we going to bother to check to see if we're hungry or not. So this is the most efficient way of expressing it. When writing, here, I'll word it another way to make sure that that's clear. If money is greater than 0, and then we're going to have a if hunger greater than 0, and then we're going to have our out statement. See out less than Snickers. If this part's not true, it doesn't do the rest of it, right? If this thing can be ruled out, it doesn't go in and check this. So you want to make the thing that proves this false more often. So you want to put the situation that occurs least often first. So for efficiency, place the expression that happens the least often first in an AND expression. What about OR? Opposite. What if I get to stay home because I am sick or tired? So if sick greater than 0 or, excuse me, bar tired greater than 0. Then print stay home. If this is inside a loop, we want to minimize it so that only one of these expressions is checked unless it absolutely has to check both expressions. Well, what is the one condition that it has to check the second expression? If the first one is true, it doesn't even bother checking the second one because it's an OR, right? And so one true is enough to convict it, right? There's no reason to go and check the rest of the evidence. If we have a true here, then the whole expression is true. And that's good news, because if this is true and we can rule that one out, then we can write our expression in such a way that the thing that happens most often is placed first. So what if my logic is like this, and I am sick 10% of the time, but I am tired 50% of the time? Then is this the best way to word it? No, because 90% of the time this is going to be false, and it'll have to come over here and perform the second check. So 90% of the time we're doing the second check when we might not have to necessarily do it. But if we rewrite it, if we say if tired is greater than 0 and sick is greater than 0, well, this one gets checked, and only if it's false does it bother to check the second one. But it's true 50% of the time. So at least 50% of the time we get to cut out making the second check. So for efficiency's purpose, put the expression that happens most often first in an OR. Place the expression that happens most often first in an OR. And that's called short-circuiting. Short-circuiting evaluation is when the rest of the expression is skipped because the first part was enough to figure it out. And does this really matter? And 80-85% of the time, no, unless you're trying to write the most efficient code. But it can actually have some side effects. And what do I mean by that? If for some reason I was an idiot and I wrote this, if a plus, or if plus a is greater than 0, no, let's not do that. Let's do if validate parentheses ampersand valid underscore location parentheses in parentheses. And these are two separate function calls. Well, if this function call returns false, it doesn't call this one. That's probably okay. But if for some reason you coded it in such a way that valid location is supposed to be called every single pass through the loop, then writing it like this means that it can be occasionally skipped. And you wouldn't want to do that. Something else, I don't think we've talked about it yet, but if you have plus a, that means add 1 to a right on the spot. Like if you had plus b, that means add 1 to b right on the spot. So if you did this, if, let's say a is equal to 3, b is equal to 7, if parentheses plus a greater than 10 and plus b is greater than 10. When you wrote this, you might have thought that it was going to add 1 to a and add 1 to b every single time. It's really a bad idea to put something inside your if expression that's actually going to be changing the values. But, so we did. We thought we were being cool. And so what happens? It starts processing it. Plus a means add 1 to a. So a is now equal to 4. Is 4 greater than 10? No, 4 is not greater than 10. It skips the rest of this expression. It does not add 1 to b. If it was critical that both of these things happened every time through the loop, they should be done separately. Right, we should have plus a, semicolon, plus b, semicolon, and then just check them, right, like that. If they both have to be done either time, I mean, through every pass to the loop. That's the only real time for efficiency's sake, or if one of these checks is actually going to be changing the state of a variable. calling a function that may change something. That's the other time that you have to worry about short-circuiting. Short-circuiting sounds bad. Captain, the engines are short-circuited. No, short-circuiting can be used for efficiency. It can speed things up by skipping the second check. All right, that's about enough of that. These notes here aren't going to make any lick of sense for future generations. I don't know whether to delete them or just leave them. Yeah, whatever. Hope you listen to the lecture and understand what's going on here. Okay, back in the saddle. That makes sense, the short-circuiting business. Checking numeric ranges with logical operators. We're going to take a break soon, but this is what we're talking about. You use AND to check inside a range. You use OR to check outside of a range. And I've already made that statement. That's sounding awfully familiar, but I teach 3 classes in a row. Have I said that? Have I said you use AND to check inside a range? Okay, so let's go to our code here and ask the user for the temperature of the water and print liquid if the water is not freezing or boiling. Freeze point of water is 32 degrees F. Boiling point is 212. So, since we want to check to see if it's not freezing or boiling, we are checking to see if something is within the range. Cout less than, quote, what is the temperature of the water? Question mark, space, greater than, end quote, end semicolon. CIN, well, I don't have a W temp. I need a water temperature variable. So, int W temp, semicolon. And then CIN greater than W temp. All right. To see if it is liquid, we are going to see if the temperature is within the range. If parentheses W temp greater than or equal to 32, man, my chair is noisy. Ampersand, ampersand, W temp is less than or equal to 212, then it's not past boiling, and it's not below freezing, so it's liquid. So Cout less than, quote, the water is liquid. Period, backslash n, end quotes, and semicolon. So if you use AND to check within a range, then the check to see if it's out of range is to use OR. To check for non-liquid, right, either solid or steam, check to see if it is out of range using OR. So if W temp is less than 32, that means it's freezing. Bar, shift, whatever. W temp is greater than 212 means it's boiling. Curly brace, Cout less than, quote, the water is non-liquid, backslash, end quote, semicolon. Now I guess we could tell them, we could check, and if it's less than 32, we could explain that it's freezing, and if it's greater than 212, we could say that it's ice. So why not? If parentheses W temp less than 32, end parentheses, C out less than, quote, ice, backslash n, end quote, semicolon. And if parentheses W temp greater than 212, in parentheses C out less than quote, steam, backslash n, end quote, semicolon. And there are other ways we could have structured all this. We could have just done if temperature less than 32, print ice, else if temperature greater than 212, print steam, else print liquid. We could have worded it like that, but the real point of this was to remind you how to check within a range and how to check to see if something falls outside of that range. We've talked a lot. Let's see if it actually works. Temperature of the water. This is really hot water. It's 300. The water is non-liquid. It's steam. And again. It's 70 degrees. The water is liquid. Once more. Check below freezing. Temperature of the water is negative 99. It's non-liquid. It's ice. Okay. So I'm going to go back to Notepad and add that to my notes. To check to see if something falls in a range, use and. Example. Because you can't write this. This is not valid computer programming. If 32 greater than x greater than 212. I think that's how we expressed a range in some math classes in the past. Grade school, junior high, high school, something like that. That looks familiar, but it's not valid programming language. So instead, you have to word it like if x is greater than or equal to 32 and x is less than or equal to 212. To see if something falls out of range, you use OR. If x less than 32 or x greater than 212. Now if you're sneaky, you could use not to accomplish the same thing, right? Because if it's not inside the range, it's outside of the range. So you could do this. If not that, then it's out of the range. I wouldn't. I certainly would not do that, but you could. I'd express it like this because looking at it like this makes my brain hurt. Alright, let's take a break. We've been here an hour and a half. I'm going to check the quizzes that have been submitted so far, and we will do a review. And I know somebody needs to leave early, so I'm going to make a Dropbox for today. Start the recording for this part. So you could do something like this. X is equal to 98. Then you could do something like this. Result equals, and I put parentheses on this part just to make it easy to read. They are not necessary. But inside the parentheses, before the question mark, I'm going to say x mod 2 equals 0. What is that doing? That's checking to see if it's an even number. If we modulus it by 2, would we get a remainder or not? If there's no remainder, then it's even. End quote. But if there is a remainder, it's odd. So what that would do is it would evaluate this expression. If that expression is true, the first thing after the question mark is copied over into result. Else the second thing, the one after the colon, is copied into it. And you can do some horrible looking things with that. I'm going to go down to the bottom of my code and I'm going to do something dumb with that. W temp less than 32, question mark, quote, or no, not even a question mark. C out less than, I don't know if this is going to work, guys. Let me finish typing it and then see if it compiles. Because this example definitely works in other languages, but I haven't tried it in C++. C out, arrow, quote, freeze, end quote, colon, \n, colon, C out, not freeze. Does that actually compile? Yeah, it does. Okay. So if I type in a temperature of -99, it prints freeze. What is going on here? Everything before the question mark is evaluated. If it's true, it does this. Else it does this. This is the exact same as if it did this. If parentheses W temp less than 32 in parentheses, C out less than quote freeze. Else C out less than quote not freeze. These two things do the exact same thing. Now I wouldn't have written it that way if I was writing it myself. I wouldn't embed I/O stream stuff inside these two things. I would just make these expressions that evaluate to something, and then if I wanted to, you know, I could see out the result like that. But here's another example of something doing something horrible. Int x equals, wait, we may already have an x. If int xx equals 1, comma, yy equals 2, comma, zz is equal to 3. Xx greater than 0, colon, yy minus, xx greater than 0, question mark, yy minus equals 2, colon, zz plus equals 3. And then print out the value of yy followed by the value of zz. What is this going to do? This is really horrible. I would never recommend anybody do this, but the PowerPoints give us an example of doing something similar to this. The thing before the question mark is evaluated. If the thing in front of the question mark is true, then this happens. So it would subtract 2 from y, making y equal to 0. Else, 3 would be added to z, but it was true. So only the first thing happened and not the second. So if we printed it out, it would print out 0, 3. 0, 3. Zero, 3 is what we got. On the other hand, if we changed xx so that it would be a negative number, so that this conditional clause is not true, if I change it to a -1, and I run it, then it does not print 0, 3, it prints 2, 6. Why did it print 2, 6? Because yy was not changed. This was false, so it skipped doing that, and then instead it did that. Now, like I said, I would never, never, never in a million years program that way. And I also would not program that way either. What I do use conditional evaluation for is things like that, where you want to calculate a result. And then you could do the result later. So you'll want to watch the last little bit of the lecture to get the review.
You recording the review part of it?
Yep. It's a weird little thing because you can always replace it with an if-else, but it lets you do in one statement what might take, 4 lines of code to do. Let's find the slide about it. The conditional operator. Here's what they've got going on. If x is less than 0, is that true? Then set y equal to 10. Else set z equal to 20. No, I don't like changing the values of my variables conditionally like that. I just don't. Doesn't mean it's wrong. If it makes sense to you and you felt like implementing something like that, go for it. I'm not going to ask you to write something like that on an exam. I'm not going to ask you to write in the, homework that does that. Going back to the quiz question. After this code runs, what does D equal? Well, is A less than B? Is that a true statement? Since A is 10, B is 20, that's true. It does the first thing. 30 gets copied into the D. So that's what D equals afterwards. Another question. Or is it the same? No, because now it's A greater than B. So what does D become now? Now that it's checking greater than B rather than less than B. It becomes 40. Since this expression is not true, it's not 30, it's 40. The second part gets copied across. Case statements. Is there anything squirrely about this one? No. What do I mean by squirrely? Whenever you see a switch case set up like that, make sure that they have brakes. If they don't have brakes, that's when the alarm bells should go off. This one is not missing any brakes, so it's going to behave just purely ordinary. And so if A is equal to 2, it jumps down here, it prints green, and it breaks. Here, we're missing the brakes. So if A is equal to 2, what happens? It jumps down here, it prints out green, and then there's no break, so it keeps going. It also prints out blue. All right. Okay, menus. We've already written a program. We did the sphere density one, right, where you chose whether it was ice or wood or aluminum and stuff like that. That's a menu-driven program. You display a menu, you give them a list of choices, and you let them pick one, and then we perform it. Menus can be implemented using if-else. Yeah. If material is equals to 1, it's ice. Else if material is equal to 2, it's aluminum. Else if material equals 3, it's gold. Whatever. So you display a list of numbered or lettered choices. You prompt the user to make their selection, and you test it. If it's true, then you execute the code. Otherwise, you go to the next expression. So it's just a chain of if, else if, else if, else ifs. Or if you're feeling it, you make it a case instead. Switch case, which would have worked for our materials program pretty well. Don't even give any examples of it. How about that? Okay, good thing we've already done one. Input validation, inspecting the input data to make sure it's acceptable. Bad output will be produced from bad input. You can do various checks. You can make sure that the number is within a possible range. You ask them for their account number. You make sure it's got the right number of digits. You make sure that the account number is all digits and they didn't enter any letters in it, right? That's kind of like reasonable. Is it reasonable? You don't even have to hit the database to see whether the account number is valid if you can check ahead and see whether it's got any garbage that they've typed in. You can check to make sure it's a valid menu choice. They chose a material not on the list, so we defaulted it. You can make sure that you're not going to do a divide by 0. You can make sure that the nurse does not say that the human body has a temperature of less than 0 degrees, right? Not support negative values. Not support having a fever of over 130, right? If nobody has ever had a fever of over 130 degrees, then it's safe to put that as a limit into our code. Input validation for a testing program. Enter your grade score. So somewhere we've defined that these constants, A, B, C, or D, probably 90, 80, 70, or 60. But we also have a min score and a max score. We're going to rule out if they enter something that's not greater than the min score and not less than or equal to the max score, we're going to print out an error message. So that's an additional little bit of data validation. So with these constants defined, go in there, they enter a test score. The first thing we do is check to make sure that it's valid. We know it's invalid if it was less than the min score or if it was greater than the max score. Assuming that that's not the case, if it's within that range, it's a range check, so we used ampersand. Then we go ahead and do the, okay, did you make an A, B, C, D, or F? Else we print out the error message. Comparing characters and strings. If you compare two strings to each other, it's actually doing an ASCII check. And that can give you some weird consequences. Like if you have this, C out, arrow, arrow, parentheses, single quote A, end single quote, less than single quote B, single quote, end parentheses, arrow, arrow, ENDL. Is A less than B? Yeah, because an A is a 65 on the ASCII table, a B is a 66. So in fact, that's true. This is getting really tedious. I'm going to start making changes up at the top. All right, so it's true. And it printed out 1 for true. It is true that A is less than B. But what if that was a lowercase a? We might think that a lowercase a is less than an uppercase B, but it's going to print out 0. Once I answer the 20 questions to get to it, it printed out 0. Lowercase a is not less than uppercase B. Why in the world would that be? That's because, according to our ASCII table, A through Z caps are between the values of 65 and 90. But the lowercase letters are 32 beyond that, starting at 97 and going all the way down here. So a lowercase a is actually a larger number than an uppercase B. Any lowercase letter is larger than any uppercase letter. And so if your MP3 player follow those rules, then all your song names that began with a lowercase letter would appear at the bottom of the list. And all your song names with uppercase letters would appear at the top of the list. Now, people go to some effort to make sure that they're not treated like that because humans don't want to see them clustered like that, right? I don't care if I named one of my Beyonce songs with a lowercase b and the other one with an uppercase B. I want them both to show up, correctly in the same place in my list. But according to ASCII order, the lowercase letters are all larger than the uppercase letters. And strings are compared like that. If we call a string comparison function, if I compare Ace against double quote Bob, it's going to print that that's false. Ace is not less than Bob. because the lowercase a beats the uppercase b. Lowercase a is a 97 and uppercase b is a 66. So this is not a true statement, so it's going to print out a 0, a false. It's just something to be aware of. Some languages are very nice, and their string class gives you a compare ignore case option, so that you can compare two values ignoring case. Hey, do you do that in C++? Compare strings, ignore case, C++. Let's see. Case insensitive string comparison in C++. What's the best way? Okay, there's a library called Boost that lets you do it. And then once you import the Boost library, you can call I equals. Interesting. Alright, it's not a simple trivial problem. In Python and Java, you can do it in one line. Okay. Unfortunately, it's not as easy as C++. But again, those languages were invented decades after C++. At least one in the case of Java, and at least two in the case of Python. So comparing string objects. We've already talked about that. The conditional operator, we've talked about that. The switch statement. We have talked about cases and switches. That's a true statement?
Yes.
Yeah, good, because we just did the quiz on it. And the break statement. There are two purposes for the break statement. The first purpose is inside the switch thing. If you have a loop, it will also bail you out of a loop. And I want us to code that into code just so that we see break in another context. So let's go up to the top of our program because I'm tired of doing stuff down at the bottom. And we're going to declare a counter. That's going to count from 1 to 10, but then it's going to bail early. So I'm going to make counter. Maybe I'll just call it C for simplicity's sake. I'm going to set it equal to 0, and then I'm going to have a while loop that says while C is less than 100. Open curly, C out, less than C, less than E and DL, and then C++, that just adds 1 to C, and then if, parentheses, C equals 12, in parentheses, break. Now this is dumb, but it's just to prove a point. It's not going to count all the way up to 100 or 99 or whatever we would expect this to do. This is going to cause it to bail out of the loop early. And so it only printed out 0 to 11 because when it got to 12, the break kicked it out of the loop. That's different from a return statement. If we stuck a return there, the rest of the code would not work. I mean, it would disable the rest of the code. It would exit the function immediately at this point, and none of the rest of the code after that point would be executed. But break just kicks it out of the loop. Break kicks it out of the switch if you're doing a case, a switch case. Remember that in this language, the switch variable has to be an integer type. Characters do work as integer types, but you can't use a floating point and you can't use a string. That's not true of Java, where you can use strings. This is telling us that switches are good for menus. And yeah, we could rewrite our ice sphere, our gold sphere thing using menus. Excuse me, using case statements. Did I make that a homework assignment? Did I say please revise your sphere program to use switch case? No? Okay. Sometimes I do. More about blocks and scope. We have talked about this. We already know this stuff. Well, we're going to hit it anyways, and then we're going to do the exam review. So the scope of a variable is the block in which it is defined, from the point of definition to the end of the block. Usually defined at the beginning of the function. May be defined close to the first use. So those are really your two choices. If you have a variable, either define it up at the top of the function or right before you're going to use it. Don't just hide it, you know, hundreds of lines inside the code but not near where you first use it. So here we created a variable. We stuck it up at the top of the function, but it also happened to be close to its first use. Now I could get all picky and stuff and say I'm going to create all my variables up at the top of the code. There's absolutely nothing wrong with doing that. Absolutely nothing wrong with doing that. And then we could document, we could add comments throughout here, right? Counter for loop, you know, bitwise, and numbers, you know, holds the result, whatever, right? You can do that. I think you can go too far with that. I don't really think there's a reason to be declaring all your variables up at the top. If this is a very long function, then it makes sense to declare it closer to it. Like by the time we were down here, what is the temperature of water? Now the reason our code gets so long is because we just keep adding to them, you know, to make examples. Your functions should not really be as long as what we're doing here. You ought to break your code down into as short of functions as possible. With this stuff about water temperature is completely different than shifting. So reasonably, if I was writing a program that had to do both with shifting values and water temperatures, I would have put those inside separate functions. And then their variables would have been declared up at the top of the function. Similarly, here's some business about comparing strings. That's conceptually not related to either of the two topics. So we could have put that inside another function. But anyways, the scope of the variable is from where it's defined to the end of the block. XX is defined here. That means it can only be used after that point. It cannot be used before it, right? I can't use XX anywhere else above that statement. If you define something within a pair of curly braces, it no longer exists outside of the curly brace. So if I had done this, if for some reason I had put this stuff all inside a pair of curly braces, like that, then when I tried to see out XX, I would not be able to do that. And there have very occasionally been times when I've programmed in that fashion where I just opened a brace even without an if or a while in front of it just because I wanted to declare some variables and I wanted them to disappear at the end. Why might you want to do that? What if I already had a variable named XX that was completely different? String XX equals wow. Right. Whatever. This is still valid code. I'm going to make an integer called XX and I'm going to play with it. I'm going to keep doing stuff with it, and then when I get to the closing brace, my integer XX disappears, but this one still exists. So when I run it, it's going to print wow. Forgive me for not actually running it and answering all those questions. It will. It would print wow at that point. So this is known as variable hiding. This one creates a new variable called XX. So anytime we talk about XX inside here, it refers to this one. You can, I mean, it's even giving us a clue. When I click on X here, it lights up that one. So this one is now hidden for the duration of these braces. And it's nothing magical about the fact that, you know, I could do this, right? If X is less than 10, right? Something like that. It doesn't matter in what context this stuff was created, or, you know, the thing that was before the curly brace. The effect is the same. This variable now masks. It now hides that one for the duration of the curly braces, and once we leave the curly brace, it's available again. So the scope of this variable is from here to here, and then here, and everything down below. It's not available inside this stuff once this XX is declared. Now, YY and ZZ in this version of XX, its scope is from that line of code all the way down to there. But once it hits the closing curly brace, it is no longer in scope. So variables with the same name. A variable declared inside curly braces are called local, or they have block scope. Their scope is the block of curly braces in which they are defined in. Now, if you define something outside of any curly brace, that's a global variable. Now, if you're inside a block inside another block, you can define variables with the same name. I just did that with that XX. When you're in the innermost block, the outer definition is not available. We can't get a hold of that XX string when we're inside the innermost curly braces because our integer XX hid it from us. Not a good idea. Yeah, I'd agree with that. All right, we're at the end of the chapter. So we will have some homework. Not a lot of it. I want y'all to be able to have a good break. But let's look at the homework. So we will write a program that asks the user for the 4 pieces of data described below. We will then print messages based on the following logic. So, first thing it's going to do is ask the user for their age, and then ask them for their years of employment. Name your variables, age and years, make them ints. All that work just as well with floats, who cares? If the age is greater than 17 and the years of employment is greater than 2, then print you get free checking. If the age is less than 17 or their years of employment equals 0, we print enroll in the training program. So those poor 2-year-old kids who march in, we send them to training. Then have it do these tasks. Prompt the user how many calls they have made this month and prompt the user for how many minutes they have talked this month. If the calls is greater than 100 or the minutes is greater than 1,000, then print upgrade the higher plan. Notice that this is a range check. This is checking out of bounds, right? So we're using OR. No, that's not quite right. It's not a range check because it's not based on the same variable. To do a range check, you're checking one variable against 2 values. Forget what I said. But if the calls is greater than 100 or the minutes is greater than 1,000, then they've exceeded their capacity. We're going to say upgrade to the higher plan. If it's less than or equal to 100 or minutes is less than or equal to 1,000, then everything's great. Stick with the current plan. But if they haven't made any calls, then we're just going to say you might as well cancel your plan. Now, honestly, this is maybe so silly that I should instead have y'all revise your programs to use switch and case. Have we done any other homework that required ands and ors? We'd better do this one. We'd better make this one our homework. Okay. So that will be the homework. I will upload it.
When would that be due?
It's going to be due certainly not Tuesday of next week. It's going to be due after the break. Yeah, the Sunday after the break.
Would this be on the test at all?
Some of this will be. But if we had not talked about and or up until today, then there's certainly not going to be much about it on the exam. Let's take a look. Let's take a look. Yeah, that's the slide that we stopped at last time. So nothing after page 40 on the PowerPoints of Chapter 4 is going to be on the exam. So everything up to page 39 of Chapter 4 is fair game. Your best review for it is just to repeat the quizzes, but let's go through it with each other. It's open book, open notes, open waving your hand and asking me for help. Alrighty. Know the difference between a bool, an int, a double, a char, and a string. For example, if I do this, if I have 1, 1.0, single quote 1, double quote 1, and true, match them up. What is 1? All by its lonesome with no qualifiers. That's an int. It's a whole number. What is this one? It's got a decimal point, so it's a floating point. You know, only floating point choice here is double. I'm not going to try to mess you up by having both float and double in the same list, right? That'd be silly. Unless I'm asking you which one's larger, right? And we know that doubles can hold larger values than floats. Okay, so if it's got single quotes around it, it is a, yep. If it's got double quotes around it, it is a string, and true false values are bools. So if you have 2 plus 3 times 4, multiplication happens first, right, guys? So 3 times 4 is 12 plus 2, so that's equal to 14. Did that make sense? I hope so. And we know that if we put parentheses somewhere, then that forces it to happen first. So what is 6 modulus 3? That means 3 goes into 6 2 times with a remainder of 0. It's evenly divided, right? There was nothing left over when we divided 6 by 3. What about 8 modulus 3? 3 goes into 8 2 times with a remainder of 2. Hope that's good. Hope that's good in people's brains. We all know what plus plus does, right? So if I say x is equal to 10, and then I say x plus plus, and then C out xx, we know what it's going to print, right? What does x plus plus do? Adds 1 to it and saves it into it. Okay, now I don't recall if we've talked about this adequately, which is the order of the plus pluses matters a very, very great deal.
Why would you write x twice?
That was a total mistake. Thanks. Okay, so if you have this, x equals 10, y equals x plus plus, C out y, as opposed to this, x equals 10, y equals plus plus x, C out y, C out E and DL. They look very similar, but they do not produce the same results. If the plus plus precedes the variable, it's the very first thing that happens in the expression. Plus plus as a prefix means do this before you do anything else. If plus plus is after the variable, it means do it after everything else is done. So let's do this one. Since it's before, it's a prefix, it's the first thing that happens. So x is 10, x gets turned into 11, that 11 gets copied into y, so it prints out an 11. How about this time? X is 10. There's a plus plus there, but that means do it as the last thing. Do everything else and then come back and increment. Okay, so 10 gets copied into y and then x is incremented. So when we print it out, it's going to be 10. So if we do this, A equals 1, C equals 2, or B is equal to 2, C is equal to 3, and then well, let's just do this. And C is equal to A plus 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 B. Now that looks horrible, and I would never write that on purpose. But then I print out A followed by B followed up by C. What is it going to print? Well, the plus plus means that, okay, let's change that to a star because that just looks too stupid. Okay. Plus plus means that that happens first, before the expression is evaluated. So what does B become? Right, so at this point, B is now equal to 3. A doesn't get incremented yet because it's a suffix. So A stays 1. So 1 times 3 is 3, which gets copied into the C. So C now equals 3. Everything is done, and oh yeah, we got to go back and we got to add 1 to A. A becomes 2. And so if we printed out A, B, and C, it would print out 2, 3, and 3. So in short, know the difference between prefix increment and suffix increment. Decrement works the same way. Minus minus works the same way. If it precedes the variable, it's the first thing that happens before anything else happens in the expression. If it follows a variable, the entire expression is evaluated, everything is done, and then it is incremented. Alrighty. Under what circumstance have we seen the pound sign used in this language? Yep, for the includes. Fancy way of saying that would be it begins a preprocessor directive, because we've used it for a few other reasons as well. We know what that is. We know what that does. And I don't ask if you know shift or not, so it just means what? Streams. That's working with the stream, sending something to the output. We know what that does. The opposite. Streams read from input. The stream insertion operator. What's the difference between those and those? This is used to mark a block of code. And these are used to group parts of an expression or to do a function call. So parentheses group the parts of the expression or enclose the parameters of a function like the POW function, whereas curly braces mark blocks of code. Is this a true statement? When a new variable is placed in a variable, the old value is replaced and destroyed. So if we do this, x is equal to 100. And then later on, I go x is equal to 1. After this line is executed, is there any way to get that 100 back? Once I print out x here, it's not going to print out 100. So, yes, it's a true statement that when a new value is placed in a variable, the old one is replaced. Right? The old variable is lost. So, there's no way to get that 100 back unless you stored it somewhere. So, common little thought problem is if you have two values, int a equals 1 and b is equal to 2, write code that will swap those two values. This actually isn't on the exam, and I ought to put it on there. But how do you swap them? You declare a temporary variable. Int t is equal to a is equal to b is equal to t. Right? It's like I have two hands and I have two objects, and I want to swap the contents of the objects. Then I need a temporary hand. Get that one to the temporary hand, I do that, and then I pick that one back up. Otherwise, you lose the values as you assign them. Why do we bother doing this? Using namespace std. We do that so we don't have to do std:" cout, std:" cn, std:" endl. If without that, if we commented that out, we would have to put std:" in front of all those IOStream operators. By putting that there, we're able to Just do that instead. So that's what the namespace is. That's the line that we have been including that lets us avoid prefixing everything with std : : avoid prefixing everything with std : : We do know that the POW function means to the power of, right? So if I do this, x is equal to POW 4, 2. What's x equal? 16. Because to the power of 2 means squared. 4 times 4 is 16. Alright, so if I have this, float A equals B times C. And if I asked you to find me a keyword in that expression, in that statement, which of those is a keyword? The float, the A, the equal, the B, the star, or the C? The word float is the keyword. Show me some of the operands. I see one operator here, ignoring the equal sign. There's an operator here, so what are its operands? Yep, so star is the operator, the math operator, and then B and C are the operands. And the equal is the so-called assignment operator, which also happens to have two operands, but I'm not going to ask you a question about the equal sign or write it in such a way that you have to know that this and this are operands for the assignment operator. So I'm going to just delete that. Remember that if you see an expression that looks like this, the formula for volume of box oh fine, maybe I should use the word block. I'm not okay. Anyways, if you see an expression that looks like this, V is equal to length times width times height in a math book, and then you were told to program that, could you do that? No, you have to put in the asterisks. You have to do the asterisks to do multiplication. Just because a textbook or Google shows you a formula without asterisks, you've got to put them in there. So if you see something written in a formula that says, you know, B is equal to 2A, we conceptually know that 2 times A, that's what that means. But if you're going to write it into the computer, you would have to do B is equal to 2 times A. That makes sense? That's called composition. When you take a formula from a textbook or online and you express it in the language of your choice, you can't leave out the asterisks. Variable names. If I tried to create 4 different variables, 2 of these are not going to work. Which are the good ones? The middle 2 are good. You're not allowed to have spaces, and you're not allowed to start it with a number. Variable names cannot have spaces or start with a number. If something has a binary operator, how many operands does it need? Binary meaning, for example, this is a binary operator because it has how many operands? 2. Yeah, it's got 2 operands, right? It's got the 2 and the A. So a binary operator requires 2 operands. Binary in this case does not mean 0 or 1. It just tells you the number of operands that it needs. All right, so if I ask you which is an integer type, is a long an integer type or a double an integer type? This is the integer type. This is the floating point type. In Microsoft Windows C, the long is an 8-byte integer, and a double is an 8-byte float. On the Mac, a mere long, you don't have to repeat the word long, is an 8-byte, but I'm not going to ask you for a mere long just because of that little bit of difference. It's Microsoft that's non-standard in my opinion. Which can hold a larger value, the long or the double? Doubles, because they contain exponents, right? If something was limited to 4 digits, then 9999 is a lot smaller than 9e to the 999, right? It's less precise. We had 4 digits of precision here, and we only have 1 bit value of precision here, but it's a much larger number. A 9 followed by 999 zeros. Does this sound like a true statement? An integer divided by an integer always gives you an integer result.
Yes.
Yeah, that's definitely a true statement. Or another way of saying it is that an integer divided by an integer gives you an integer rounded down. Also a true statement. Casting. 3 ways of casting values. Casting is forcing something to fit into another data format. Like if you have a long and you want to store it in an int. Or if you have a float and you want to store it into an int. Like float f equals 9.9 e to the 99, right? And you want to, well, that's far too large to store in an int, sorry. So I'm not going to do that. How about just 9.9? If you want to store that into an int, several different ways, 3 different ways. I is equal to I and t parentheses f, that's one way. I equals parentheses I and t in parentheses f. This is the C style. This is the old C++ style. And this is the new C++ style using static cast. Static underscore cast angle int end angle parentheses f in parentheses. Now that sure is wordy, but when do you use cin.getLine? If the input's going to contain spaces, or every time you want to read into a string? Yeah, you use getLine if it has spaces. Otherwise, it's just a lot of trouble that you don't want to mess with. What does setW do? It's an I/O manipulator. What does setW do? Sets the width. Like if you do this, cout arrow arrow setW to 10 arrow arrow x. X will be padded out to 10 spaces. And I'm sure that there's an operator that dictates whether it's left padded, left justified, or right justified. How about set precision? If you do this, cout set underscore precision. I thought I was spelling that wrong. 2, arrow, arrow, fixed, arrow, arrow, 9.11111. What's it going to print? Yeah, it's going to limit it to 2 decimal places. One of these, set W or set precision, you have to call every time you want to print the data out. And the other, you set it one time and the value is sticky. It just keeps that way until you ever decide you want to change it. Is set W the one that has to be called every single time?
Yes.
That is a true statement. Set W has to be called before every piece of data to be formatted. Set precision only has to be called once unless you're going to decide to change the number of decimal places. All right, that one is from chapter 4, but it's only from today, so we're not going to do that one. Do that one. All right, that's about it. If you do the quizzes again, and this part seemed pretty easy, then you're going to ace it. I'm not planning on making you write any whole programs, by the way. Just little lines of code like in the quizzes. Although I sure would like to make it support more than just one line, so I'm going to figure out how to do that. All right. If y'all have any questions over the weekend, let me know. Otherwise, have a great weekend, and I'll see you on Monday. Yes. Yeah. And if you can't be here, let me know, and I'll set it up so you can take it at the library. I would assume that everybody in here is going to be here, but maybe not.
Can I use our personal laptop today?
Yes. Yeah. Not. That's the reason you want to take it here rather than go to the library, is so that you can do your personal stuff.